Okay, let's go ahead and get ourselves started for tonight. Thank you for joining us on Halloween evening. We hope to have a entertaining and action-packed time for you. Hopefully not too spooktacular. We'll go ahead and try and keep it fairly straightforward in terms of what's going on here. We have a couple of big things we want to talk about tonight. We want to keep on pushing on the notion of creating custom geometries, and I want to show you just kind of really one of the most powerful things you can do with your components. We're going to talk more about adding formulas to them to really make them quite smart so they respond very nicely to the geometry and the lengths and all the conditions you try to use them in. And there's some really cool stuff we're going to do in terms of showing how to use formulas for these things. I will preface this by saying that there's no expectation that you will use formulas to make incredibly smart components as part of what you're turning in. So, this is really kind of extending your knowledge, letting you know what's available and all that type of stuff. But don't think that because we're showing it to you, oh my God, my components aren't, using formulas, I better go back and add something like that. Because really, for the purpose of tonight's assignment and after class, was going to be office hours to kind of help you with some of the last minute things you might have going on there. Really, as long as you have a couple of different components, however many you're signed up for the class, that are stretchable, what do we want? It should have, 2, 3, 4 pieces. It doesn't need 20 pieces to it. Okay, relatively simple. Has some stretchability, maybe the length and the width and the height. It doesn't have to be completely parametric in terms of doing a lot of different things. Just kind of a little bit of stretchability, maybe some material. Yeah, that's cool. You're fine there. You don't need to kind of go all out. If you want to go all out, feel free to, but don't spend all night doing it or something like that. Like everything, it's so hard with all these projects to know when to stop because you could always make them better. So just know that you're not expected to, but have fun if you want. Okay. The second thing we'll talk about today is materials, and we've talked a little about materials in terms of assigning materials to different elements. We'll look at sort of the whole hierarchy of how that works and how you define new materials. So if you have some fantastic image of a type of siding or just some fabric or something that you want to apply to your components, you go through and create your own materials just using bitmaps. So anything that we could snap with our camera or that we can find on the web, I'll show you how we can create some new materials. Okay. Lastly, we'll be talking about rendering and the whole notion of visualization and really pushing into the notion of ray tracing, where we not only apply materials to get some sort of photographic image wrapped around an object, we actually start getting to be very precise about how light is coming into a building or hitting a building, how the shadows are going to be hitting, and just the precise amount of light hitting each of the different surfaces. So it's really where we move from these relatively cartoony views that we're working with now to really getting something that looks much more photorealistic. And ultimately, if you're going to be presenting your designs to people, it's nice to kind of be able to take them to that next level and say, hey, this is really what it's going to look like. It really, but it's kind of a very natural extension of what you've been doing so far. You'll find it's really not a very big stretch at all from where you are today. So, in terms of getting started, we'll start with this whole notion of parameters and the different types of parameters you can add. And we've been looking at adding a lot of length sorts of parameters. We've looked a little bit how you can add a material parameter or yes or no parameter. We're going to go to extend that a little bit now to actually say that in addition to the parameters, we can also start using formulas to relate the different parameters together. So things like, that the area of something is going to be the length of the width, the volume is going to be sort of related to something. You can go through and create different relationships between the length and some of the other parameters to really go through and control different things. So let's think about how that might be useful. So if, for example, you wanted to go through and create a box of constant volume or something like that, okay, you could go through and say that, that the height is going to be, let's just sort of think in here. Let's say we have a parameter called volume, and you put a value in there like 30,000. Good for square feet too. But we could say that the height is going to basically be equal to volume divided by whatever the length is times the depth. And what it'll do then is no matter what you do, it's going to try and maintain a height relationship based on whatever the length and the depth are. So if you resize anything, the height will sort of adapt itself to try and maintain a constant volume. Okay. Yeah, it's a lot of different things we can do in terms of trying to maintain sort of simple relationships between. We talked about, for example, on this table, if we wanted to have some proportionality between the two different things. I actually learned there's a different function there called roundup, which we'll use in just a minute. Okay, but we can relate that, actually, that's wrong. The length would be, actually, I really messed it up. We'll say width is going to be equal to like length divided by 4. Something like that. We'll just leave length down over here. But we can create some sort of proportionality. So if you want the table to be a 2-to-1 relationship or a 3-to-1 relationship, whatever it is, we can sort of set up a formula to make sure those are always defined. We could also go through and do things like for that turntable, give it a proportionality. So anything that we want to have related to each other. There's another type of object that I want to talk about that I think is really sort of very, very useful just to show you how smart these can get to be. And I found an example that I really kind of like that's based on sort of a truss that you can use. And we use these in our framing. Oh, yeah, I'm going to pull out some new pens. Okay, bring your own. Okay. And it looks something like this. There's a type of element that we can apply. Actually, let me show it to you, and I'll start drawing it and sort of decomposing it a little bit. And if you want to follow along, please jump on out to the coursework website and download this little project here. It says Smart K-Joist Component Example. Okay, that has this little example built into it. I'll open that up over here. Open in Revit. Let's see what it says. The K-joists, a lot of these truss-like components are actually pretty smart. They're built with just a little bit of intelligence, and we're going to take it apart and decompose it a little bit, see if we can learn something from it. And again, that's always a very valid way to approach this. Never be shy about opening up someone else's component, trying to understand it, and then we'll say borrow and influence your design in terms of what's going on, because people have learned a lot of interesting things. And you might as well benefit from what other people have done. Cancel out of that. Might be me. Have to be used by another user. I'll think about that in a second. Oh, I think I have 2 instances of Revit open right now. There we go. So this is the little component I have in mind. And let's talk about how it works and how it's run. So that's actually considered a piece of framing. And the nice thing about it is that it's actually pretty smart about how it is kind of working. If we're putting in framing and we put in, for example, an I-beam or some sort of wide flange section, that's actually a little bit easier. I'll put in a beam, for example. I'm going to put it at level 2. I'll just put it over here and drag it over to this side. Oops. I always forget to do this. I keep on forgetting to change beam, change the type. I could change the type on it after the fact. I just want to draw it for you. So I'll put it in here. Okay. The nice thing about the I-beam is if you want to think about it in terms of how we've been talking about elements recently, it's a sweep. Okay, you could think of it as an extrusion. It's actually a sweep, which it can be an extrusion if you only do it in kind of a very straight path. But what happens is, as you're working with that sweep, as you're placing that, we'll stretch a line from one side of the building to the other side of the building, and it'll make it perfectly sized towards that. If it's 39'2", it'll make it 39'2". If it needs to be 39'3", it'll make it 39'3". It's pretty easy in terms of going through and creating that sweep, because any arbitrary length, it'll just drag the profile along. An object like the K-joist, though, is a little bit different, because it's not just sort of it's not a continuous line. You see, it's actually made up of all these little bays, all these little kind of cross sections. Let me orbit that around. You'll see that a little bit better. All these little V-shaped sections, and what's kind of interesting as a part, you can't just arbitrarily have a half of one or a quarter of one left over. We always have to resolve the length so that it always ends with one of these funny elements here that kind of has it rest up on the building sides. So, you know, those little like ledgers that kind of stick out there. So it's a little bit more complicated about how you have to go through and build that. Now, this component, it turns out, is pretty smart. If you want to grab it and kind of drag it around, you can choose it, and you can try stretching it, and you'll see that no matter how wide we stretch it, it always seems to be just right. Okay, and that might seem kind of magical, but it always adapts itself, so it's going through and giving you just exactly what, some even or some whole number of these intermediate bays and these two little end sections, and it's always adapting itself. And if you want to sort of see just what it's doing, we can even go looking down. We can choose it and look at the properties. Down at the bottom of the properties, you'll see that it has several different things going on there. It has some notion of a panel and a number of panels. So in this case, it's saying that there are 14 panels, each of which are 2'11" and some change. And if we went through and counting them, like, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's do the high, pointing in the other direction. You know, it has a distance. It's somehow going through and computing a couple different things. If we stretch that just a little bit further, okay, let's go on down. You'll see it's still giving me 14 panels, only they're a little bit longer. I'll stretch it further still. Now there's 15 panels. Okay, and the length is a little bit smaller. So it's doing a couple different things. It's adjusting the number of panels, and it's also adjusting the panel size so that it always ends up with some whole number of panels. There's never a partial panel in there. Okay? So it's really pretty interesting how it does it. Let me kind of open it up and we'll decompose it a little bit, see what we can learn from it. If I choose this, or any part really, I can always say edit the family. That's the quick way to get at it. Let's take a look at this thing. So in many ways, although it's a pretty complex object, it has a lot of things that are very familiar to you. For example, if I open up the views and go to the floor plan view, this part should look fairly familiar to you. It's got an overall length and a parameter which is indicating the overall length. It has some equality relationship on each side of the center line. Okay, and that's just all about, no matter what the length is, grabbing that length as a value that we can call length, and then making sure it always stays centered. Okay. It has some endpoints out here. But yeah, let's have to look at it from this view. Let's look at it in the elevation view. We'll see a little bit more about how it's constructed. And I'll zoom in on one end of it. Maybe even up here a little bit. There's some sort of notion of what it considers to be a panel, and it is one of these whole V-shaped sections. Okay? Then there's this notion of what it considers to be an end panel. And there's actually sort of a relationship between those different things. If I go opening up the family types, we can actually see how all these different things are defined. So it does have this notion of an overall length. Okay, that's the 24 feet. That's in this, before we place it, that's kind of the standard size. It also has a depth right now of 1'6" or 18 inches. And based on that, it's going to go through and compute some different things about how it wants to draw itself. Let's kind of talk about it. So it's got an overall length. It also has what's considered its depth. So somehow, and then it's this thing. Not too bad. Okay. So depth is this. it seems to have this notion that, okay, we have length and depth. Let's see what we can find out here. The end panel distance is 2 times the depth. So there's some notion that the distance that I can go here is going to be 2 times the depth. Okay. And that's just based on something about the geometry and the maximum angle we can achieve. That's just sort of a physical constraint. They're always trying to design it so that's 2 times the depth. Okay. So the same thing's going to happen over here. It's going to be 2 times the depth. They're going to go through and say that there's a panel array length. So if this is the length, somehow there's another length that is the distance between the funny end panels and where it's going to divide it up regularly. And it's calling that the panel array length. Okay. And that is just the length minus 2 times the end panel. Make sense? Then once we have that panel array length, we actually get to figure out, just what is the size and how many of them we can fit in there. So the panel size is the panel array length divided by some number. The array length, okay, divided by 2 times the depth is the number of panels. So what it's doing is taking this thing, and then it's dividing that by panel array length divided by 2 times the depth. And figuring out, okay, based on this, I can go through and break it up into a discrete number of panels. And then based on that number of panels, it's dividing the panel array length by that number to figure out what the dimension of each one of these are. So it's kind of basically figuring out the number of panels. And it's figuring out an individual panel length. Now, as a 24-foot section, it all looks pretty even in terms of the panel and the end panel and all that sort of working out to be just exactly the same. If I change that, for example, and make it 25, you'll see that it changes around a little bit. The end panels are still 3 feet. The individual panel is going to be 3 foot 2 because I have 6 at 3 foot with 6 spaces to break up that 19 feet by. Same thing here if I change it to 26. You see it's kind of changing. Now I can actually fit a 7th hole one in there, but they have to be less than 3 feet. So there's sort of a relationship between all those things. So it turns out to be a pretty smart part. And I really show this to you more as an example of what you can do. We're going to kind of do a much simpler example. But this whole notion of being able to kind of take care of controlling the relationships between things, compute how many of an object you might need to kind of handle a length, and then ultimately have the geometry reflect that. It's pretty sophisticated. But if you can do something like this, you can really create almost anything in terms of being able to size things up. So let me say okay to all that, or just cancel to all that. That's how that one's constructed. Let's see how we can apply the same sort of lesson. And I am going to do it in a different context. We're going to go back to my table that has the turntable on the top and see if we can go ahead and build that. And here's my essential things that as I'm starting out my design that I want to sort of have happen in here. I want to go through and have some relationship between the length and the width. So I don't know. Let's just say that arbitrarily I want to always have a 3-to-1 ratio. And we could change that, but that's my design consideration right now. That's somehow lucky. I want 3-to-1 in here, or no more than that. Okay, I'm going to go through and make this funny little turntable piece, and somehow the size of that piece I want to have related to the width. I don't want it to get bigger than the width. I want it to be some ratio of the width. So we'll figure out what that. So I got this sort of turntable radius. The other thing I want to do with this whole thing is really, as the table gets bigger and bigger, I want to start thinking that, let's say that we could never have a leg more than 4 feet away from the other one. So if the table is 4 feet, it'll have 2 legs. If it's 6 feet, it'll have like 3 legs in there because I never want the spacing to get larger than 4 feet. If it was 12 feet, it would have like 4 legs. Is that right? Yeah, something like that. Or on a side. That's going to be 8 then. Okay, whatever. I can't do that. But you get the idea of where we're going with it. Okay, beauty. Then let's go ahead and implement this, because it's actually, you are closer to being able to do this than you think. So it's all going to start with creating for yourself a new family. And we'll create a furniture family. Change those over to thumbnails. I'll switch it back. Okay, now I'm going to race through the first part of this because you've seen me do this a couple times now in terms of just putting the basic constraints down. Well, that might be a good refresher if you're having to do this later tonight. In terms of saying that I want to create this big rectangular surface, and the way to do that, and just bear with me for a minute, we'll hopefully make it pretty easy on you. We'll put some reference planes on the back. I'll put some reference lanes on, oops, that's a little bit non-square. Put some on the side. And what we're going to do is just put some annotations on there. We'll put some dimensions that let me go through from side to side. I'm going to call that one the length. I'll put one going in the other direction. I'll call that one the depth. Add a parameter. Let's make that the depth. Okay, the putting of the equal constraints, just to go through and make sure that it doesn't uncenter itself, or keeps itself centered. I'll put them on this side. There's really no difference. I could put the dimensions anywhere. As long as they're in there somewhere, they'll apply. So I just tend to put them wherever I think they'll be out of the way so I can see what's going on. Beauty. Okay, so at this point we have this thing which will hopefully just be a nice rectangular box of some type, and that'll be our tabletop. To go through and put the tabletop in there, we'll make an extrusion. Again, using the funny idea of, instead of having it kind of go right to the lines, using the align tool to lock the edges. So align and lock. Align and lock. Align and lock. And align and lock. Okay, looking pretty good. I'll make this, at the top side, turns out I was trying to think about exactly the precise height of a table, like a dinner table. I think it's 28 inches. It might be 26, but I'm pretty sure it's 28, which is 2'4". And I'll give it about a 2-inch width, so I'll say it goes from 2'2". So hopefully that's looking pretty good. If we wanted to put a material in there, we could do that too. I'll leave that out for it. Well, I'll do it now. Put it in here. I'm going to add a parameter. It's going to be my tabletop material. I'll make that an instance parameter so I can change it real easily. Okay, and now I have a parameter to go through and control that too. So that's the basics. Let's kind of finish that off and see how we're looking. So I'll open it up in 3D. Not too bad. Okay, we can flex it. So great. Let me kind of shrink that up so we can see a little bit better. So I want it to be 9 feet. I want it to be 2 feet. And that part's looking incredibly familiar, hopefully, as you work with this now. Okay, let's start adding some formulas to this. One is the notion that we want to have a relationship between length and depth. And that's really easy to add. I could either say that length is going to be depth times 3, or I can say that depth is going to be length divided by 3. Either way will work. It doesn't really matter. Just as long as you sort of have the relationship built in one way or the other. I'm just going to make that length divided by 3. Notice it'll change its value right away. But at this point, those two things are locked together. There's actually a constraint between them that'll always be honored. So if I go through and put in a length of 12, it'll change it to 4. If I put in a depth of 6, it'll change it to 18. So either way, doesn't really matter which side you push it from. Just go ahead and push it from one or the other. Okay, so let's pause there for a second. So far, so good? Pretty straightforward? Excellent. Okay, let's go ahead and put this little circly guy in here. Let's zoom out again. Oh, the table's way over there. Let me pull my dimensions out just so you're not confusing the dimensions with the table. Okay, table's in the middle. We're going to put this little circular object in here. I'm going to try something. Give me just a second to try something to see if this will work just right. I'm going to create an extrusion. Let me try this. Hang on just a second. I meant to test drive this beforehand. Hang on just a second. And if this works, I'll let you know what I'm up to. Nope, it's not going to do it for me there. Okay. I'll show you the other way. I was looking to see if I can sort of thwart a problem before we get there. Okay. We're going to create that little turntable. And to create that little turntable, I will say create and make an extrusion. I will make a little circular extrusion. We haven't played with that very much yet. But I'll hover right in the center there. You notice that right now I'm right on that center. It says intersection right there. It thinks that's the point that the center of the circle is going to be associated with. So hopefully, if the center moves, it's going to kind of move, well, whatever. That point will move with it. But it's currently hovering to there. Let's click right there. Oops, I missed. Okay. Since I missed, what's going to happen is as the table resizes, it may not kind of lock into the place where we want it there. So I'm going to stop and do that over again. Going to go right over here. See if I can get right on that. We'll talk about a better way to control that in just a bit. But I'm going to put some sort of circle in here. This is my little turntable, like a Lazy Susan. At the top here, I'll make it go from, let's say, 2'5" to, 2'6" is fine. A little bit thinner. We can give it a material also. I'll say give it a nice material like the turntable material. Okay, we are ready to close it on up. So at this point, that turntable is completely independent of the size of the table. If I go through and resize that table again, okay, the turntable's staying the same. So if I wanted to create a relationship between the size of the turntable and the depth of the table, the length of the table, that is easy to do. We'll just say, cancel out of this. We're going to need to actually put a parameter in here to drive that radius. And to do that, we'll choose the turntable, and we'll say edit the extrusion. And what we're going to do is put a radius on here. Now, the hard part about like circles is you can't kind of put reference planes in there to drive the front or the side to side and something like that. You have to control that through a radius. So there actually is a type of dimension, annotate, that does radial dimensions. Did I get it? There we go. So I have this dimension in here. It's currently set to 2'5", something like that. But in the same sense that we can grab any other dimension and turn it into a parameter, we can grab this dimension and put it in, turn it into a parameter. So I can choose that guy right there, and I'll say add a parameter. This will be the turntable radius. Okay, and to establish the relationship, I'll open the family types, and I have this turntable radius. We can put in some relationship we want it to have to depth right now. For example, if I want it to always be depth times 2/3 or something like that, I can do that. Oops, that's the radius. I'm sorry. I should probably make that depth times 1/3. Okay, Let me go ahead and try some other ones. I'll make that, so you see the turntable radius is 1'4" right now. If I change either the depth or the length, it'll just kind of keep on adapting. We have sort of a simple relationship here. It's just 1/3. Okay, so it's always going to follow that. Now, just to make your life more interesting, you don't just have to have a single relationship. You can actually have a couple of different relationships that change based on some different things. So let me talk about that for a second. We got these sort of simple syntax examples. They're kind of pretty good for getting a lot of the functionality you want out of this. But you can actually go through and, okay, addition, subtraction, that kind of stuff, logarithms, exponential functions, trigonometric functions, those are all available. But they actually have cool things like this. You can set up little if conditions. So if this is true, do something. If that is true, do something. Okay? So we can set up something, for example, if, we want the minimum size that that table can be to be like 3 feet wide or something like that. We can say if the length is greater than something that would keep it above the 3 foot wide depth. Use the formula. Otherwise, just use the set number 3. That way you'd have a threshold. It wouldn't get any smaller. Let's try that for a sample. So we're hanging around over here. Let me close that guy up. So if I wanted to go through and put kind of a threshold in there, I could say the depth is equal to, okay, let's see, hang on. If length over or divided by 3 is greater than 2 feet, okay, then let's use length divided by 3. Otherwise, just go ahead and put in 2 feet. So you see what that's going to do? It's going to have a minimum to it. If the threshold would actually make it less than 2 feet, it's going to just stop at 2 feet. Okay, so let's think about that. So let's see if we can drive that and make that happen. So if I say that, okay, what would be 2 feet? It's 3 to 1. So at 13 feet, the depth is still 4'4". At 12 feet, the depth is 4. I just said make it 2. Okay, let's go down to 9 feet. 8 feet. Okay, 6 feet. Okay, that's right at the threshold. Still I'm doing our 3 to 1. 5. Okay, so now it's no longer 2 to 1. 3. Again, no longer 2 to 1. So we just have a cap in there. And every once in a while you want that. There's sometimes you don't want to exceed a limit. You don't want to get bigger than a limit. Okay, so we can do something like that. The other way I was going to suggest using that, though, is we can go through and even have like a different proportionality. So if, for example, if the length of the table is greater than 12, let's do 3 to 1. If it's less than the length of the table, or 12, do 2 to 1 or do 4 to 1. We can sort of change different sort of conditions. We have different sort of proportionality based on what you want to do. So let's kind of show you what that might look like. So over here, well, I'll just do it to this one. If the length is greater than 10 feet, we'll use depth divided by 1/3. If it's less than 10 feet, okay, instead it's going to be just basically depth times 1/2. Oops, I forgot to put a parentheses at the end to close that. So now we have a different sort of relationship. So let's see if it's 10 feet. Okay, it's depth times 1/3, so that's why I got the 1'8". If this is now 12 feet, okay, it's depth times 1, unless if length is greater than 10 feet, depth times 1/3. Oh, I'm going the other direction. That is 1/3 now. Let me switch it the other way. If the length is less than 10 feet, so if it's 8 feet, the depth is that, it's 1/2. So I'm getting the right relationship in there. So yeah, we can play games and just kind of really set up any sort of constraint you want to. And there's really a lot of power in terms of doing that. as 1/2, actually at 1/2, then it would actually match half the table and be right up there. That's not a very good relationship. Let's go ahead and change it instead. I'll make it depth times, instead of 1/3, 3/8 or something like that. That might be a little bit better. Okay, so whatever it is you want to do. So the next step in our adventure here might be to go through and add these legs to the table. So let's talk about those legs for just a second. The legs are actually kind of amazingly similar to each other, more than likely. Okay? And because they're very similar to each other, I might want to try to array them. I might want to make some sort of copy that, if anything happens to one, it'll sort of affect all of them. Okay, but let's talk about, I'm going to create something, get into a hole, and then we'll go ahead and fix the problem. It's really the way I'll approach this, where I'm going to go through and put in here, let me go through and create, well, actually what I want to do is actually I want to put in some reference planes that are going to indicate the leg locations. Let's start with that first, because I don't want to sort of put them kind of arbitrarily. I actually want to be able to have the legs follow the bounds of the table around. So what I'm going to do is draw some more reference planes. I'm just going to draw it on the inside of the table here. And I'll put some over here. What these are, think of those as being the center lines for the legs. Oops, of course that one's on the outside, which is not very good. Okay. And now we can put some relationships in there. If I want to control the locations of where those centers of the legs are going to be, I could put in, some dimensions that look something like this. Now, I can choose that, make that like 4 inches, 5 inches. Okay. I'm just going to put these in as fixed dimensions. You could go ahead and put that as a parameter. You could add a parameter if you want to be able to control how far in and how far out the legs are. But up to you. Let me annotate in the other direction. So I'm going to be careful about this. I don't want to grab the edge of the table. I actually want to grab the reference line. If the reference line is kind of hiding, let me kind of show you what's going on here. I'm over the edge of the table, but it's still the shape itself. It's the geometry that I've grabbed right now. I might have to tab to get to the reference plane. That's what I really want to grab. Again, I'm the shape, and I want to get the reference plane. Oops, missed that. And just arbitrarily, I'm going to make those 5 inches and on both sides too. That wasn't right. Okay, so far so good. Get a sense of where I'm going. Okay. Before I place those legs there, I'd really like to resize the table and make sure those lines move properly and they're always staying 5 inches in. So I'll do that by just kind of flexing the table a little bit. Let's say it's 6 feet wide instead. Okay, looks like they're holding the 5 inches. That's looking pretty good. Okay. Let me pause there for a second, give people a chance to catch up. Is anyone having trouble? You doing pretty good? An issue? Mr. Raj, let's go see if we can figure it out. Help is coming. Let's see if we can work out. And as you're looking at that, we'll start talking about how we're going to approach these legs. Now, there's a lot of ways we can approach these legs. We could go ahead and just make an extrusion, okay? And I actually have 4 different legs, so I can try making an extrusion that has all 4 legs in it all at once. Now, the problem with doing an extrusion that has all 4 legs in it all at once is it won't resize nicely because those 4 legs will still have the same positions relative to each other. They won't sort of move so well. So I don't necessarily want to go through and do it that way. I could go through, and I'll just do this to kind of show what I'm not going to do ultimately. I could go ahead and try to create a leg over here. And I could come over here. Oops, I'm going to close that one because I don't want to have them moving together. I want them to be able to move independently. I can make another extrusion kind of over here. Now for these extrusions, I really do need to set their height too. I've sort of been ignoring that. Create another one over here. Well, we'll leave it at that for now. For these two things, I could go through and put them in as, I think it was 2 foot 2 was the bottom of the table, but let's be smart about it because they're kind of hanging around over there, looking not too good right now. What I would really love to do is actually have a parameter which says what the table bottom is right now. Okay, yeah, and just be able to kind of lock to that and have the legs always sort of match the table bottom. So to do that, again, just some reference planes. I'm going to have something up here which will be the table top. I'll have something over here will be the table bottom. Okay. What I'm going to do is actually set up two parameters here. One that I'm just really going to use to report a value. So I'm going to put one dimension that's going to go to the table top because as I start resizing this, I think about specifying it in terms of the table top height. That's the way I really think about it, not the table bottom height. But I do still want to be able to get to the issue of what the table bottom is. So I'll say that's table top height. Okay. I'm going to go through and create another one for myself, just to be table bottom. And why am I doing this? It's really just so I can sort of control that. I could and access that value. I could lock in a value, but I'm going to do it this way. It's going to give me a little more power in the end. Say, okay, that's going to be, add a parameter, table bottom height. So what do we want to have now? If I know that I want those two things to always be a set distance from each other, I'm going to put a formula in that's going to relate those two. So I'll say that table top minus table, or table bottom is table top minus 2 or something like that. Just some simple relationship in there. Let me align the table top to that. Let me align the table bottom to that. To get figured out?
No.
Nope.
Yeah, you're not able to.
Not able to? Anything I can help with, or what do you think?
It was showing some additional constraint.
Oh.
That constraint is not satisfied.
Oh, this has happened to us. Even this morning it sort of happened. If it says, oh, additional constraint cannot be satisfied, just click remove. Okay, and try changing it again. If it gives it to again, say remove. Eventually we'll remove enough constraints that it won't happen anymore, and we'll look back at the object and figure out, is anything that we care about missing? Because every once in a while, you end up locking things accidentally, so you have double constraints on the same thing, and it confuses it. It's just not sure what to do. So, like if I had two lines like right on top of each other, it might complain about that. So generally, when you get this, it's over-constrained and you can't, it doesn't know what to do, just say remove and see what happens. Try it again. See if you can liberate it to the point where it thinks it's okay. Then go back and look at your object and figure out, what did I lose? So a lot of times you didn't really lose anything, you just got confused and it's sort of overly constrained. Does that make sense?
Yeah.
Yeah, it's kind of weird. This is almost why I tend to go through, even here I put two constraints on it at the same time. Okay. That's sometimes why I always do one at a time, because that way I can tell exactly where I broke it. And then I can back off that last one. Don't go ahead and put 15 on and then test it, because if you need to back off, it might be one of the ones in the middle and it's really hard to figure out which one it was that broke. Okay, so try that. So over here, I'm going to say that my table bottom is just equal to my table top height. Has to be spelled with a capitalization just the same. Minus 2 inches. Okay, so now if I make the table top 2 foot 2, it'll be 2 feet. If I make it 2 foot 4, look at that. Now, why do I care about all that? Because what I really want this to be is over on these extrusions, I want to go through and align the bottoms to the bottom. I'm going to align this thing again to the bottom of that one. Oops, do it again. Aligning this one here to over there. lock that in. The bottoms are taken care of. We actually sort of have a choice now about what to do with the top. You can introduce constraints a lot of ways. You can introduce constraints by locking the reference planes. You can introduce constraints by putting a formula in there. So for the tops, I could lock the top to that green line there, and that'll do it. The other thing I could do is I could actually sort of say that the top is determined by this parameter, bottom height. Either way will sort of work. It's the same basic issue. It's accessing the same value. So let's go ahead and I'll align. That'll work. The other way I'll do something different. I'll just show you the other way over here is we can say that the end is equal to the table bottom height. And that's really just two different ways of getting to exactly the same thing. I can either lock it or I can sort of say that I'm going to do it to the constraint. And that's my little lazy Susan on top. Now, this whole method's actually working pretty good in terms of what's going on. And the next logical thing I would love to do is say that, hey, as this thing moves out and kind of changes, that I can take this little guy over here and just array them. I'd like to just kind of array them along. And so, you know, if I need 3, if I need 4, if I need 5, it's just going to copy an array and kind of make a nice collection of them and do that. And that would almost work. You know, I used to try and do that, and I would get so frustrated. Because let me show you what would happen. I'll draw it. It's probably easier that way. I used to tell people, great, let's go ahead and make a framed wall. So we have the top, we have the bottom. These are like reference levels. Actually, let me draw them in green, since that's the way they sort of look for us. So I'd say, great, there's a bottom, there's a top, and we would go through and we'd create some sort of a piece of framing, like a stud, or just some sort of piece that's stretching from bottom to top. Super. We want to create another one, so what we do is we create an array. So we go through and array them so we get a bunch that look like this. And everything's looking okay. Super. Okay. The way arrays are defined, secretly, you don't know it, but they're defined such that it has sort of a starting point and it has an ending point. Okay? It's the way it sort of works mathematically in terms of how the program is generating them. So what would happen is this. You'd go through and you'd say, okay, I got a smart object, no worries. I'm going to make the wall this tall as opposed to this lower length. Okay? And what would happen that would frustrate you enormously is it would do this. Okay, that would come up. Okay. But that would happen. Okay, and this would come up, and that would happen. And this would come up, and that would happen. Like that. Okay. So what it was doing was it was saying, okay, I'll take that starting point, I'll take that end point, I'll stretch them all around, but it wasn't changing the length. It was actually just kind of keeping the set length of each of those different elements and just kind of stretching the start and end points, okay? Which was incredibly frustrating. You're like, this can't be right. This is really bad. Okay, you need a better way to do this. So, finally figured out what it is, and it actually sort of makes sense. And let's talk about that. As you go through and create this table out of all these different parts, okay, you can assemble it just out of extrusions and things like that. You can actually go through and put parts inside of parts. You can nest them together. And it turns out that's a stronger way to do it. It gives you the right behavior if you nest a part inside of another part. Extrusions, it turns out, are kind of a little bit weak in terms of how the lengths are determined and what they stick to, and it's a little hard to control. But if we go through and make the legs as separate parts, okay, you can actually give it a numeric value, put a formula together to control what the leg height is, and it'll always be right. It'll do the right thing for us every time. Now, that may seem a little bit strange that you have to do it that way, but it actually buys you some power. For example, if you were a furniture manufacturer and you had certain leg parts and you had certain wheel parts and a whole library of different things that could be assembled together, you probably do want to make all these separate little pieces and assemble them so that any object can subscribe to little subcomponents to build the assembly, but you can actually change the subcomponent and it will change all the different instances. So it's actually more powerful to do it that way, but it also takes care of our arraying problem. So let's think about that. Because what we want to do is ultimately array those legs around as opposed to drawing them individually. You know, this will sort of work fine in terms of, let me just flip it back to 3D. Yeah. This is going to work fine in terms of, I think, if I put the length in there, make it 12 feet or something like that. Yeah, it kind of did fine. Although, no, it didn't do exactly fine. It sort of stretched things in a weird way back there. So it actually made the leg very fat there instead. But we're going to show you a better way to do it. Gives you more control. So I'm going to take those legs out. Here's what we want to do. We are going to create a subpart, a little part that's just nothing but the leg. It sounds kind of goofy, but it'll work. And to do that, we're going to create a new family. It's also going to be a piece of furniture. It doesn't have to be a piece of furniture. But it looks very much like we got started before, and this piece is going to be incredibly simple. I'm just going to make a nice little round shape and give it a height, and that's going to be my leg. Very simple as a starting point. So, for this round shape, I can decide how much control I want. I'm just going to make a little nice round leg. Yeah, something like that big. I can make it a parameter if I want to, but I'm just going to make it a set 4 inches right now. Finish that up. If I look at it in the floor or in the elevation view, you see it's only about 1 foot tall right now. I want to basically put a parameter in here that'll let me control the height, okay, that I'll be able to address later. So how we do that is over in here, I'll draw a reference plane. Okay. I'm going to add a dimension to it. I'm going to call that table leg height. And then I'm going to lock to it. Now, there's a lot of different little steps in there, but I'm hoping that'll look pretty familiar to you. So, sounds really dumb, but that's all I did. I just created a separate little part of that. Okay. That sort of makes sense? Okay, so I've made a separate little piece. This is going to be called my table leg. I'll just save this one away. I'll put it out in my 120 folder, if I can find my 120 folder. Okay, with my little table leg, we are ready to load it in. This is the other thing now. So parts inside of parts can be inside of parts that are inside of other parts. You can really, recurse this as much as you want to, or recurse this, I guess is the proper word. Let me go back over to, well, actually, I'll show you the quickie way. I've saved it. I can go in to the other thing and say, insert it, load the family, okay, and bring it on in. The quickie way is, since it's already open, the other family's already open, I can't just say load in, and I'll load it into that other piece. That just saves you a step. So doing this, it's just the same as saving it and loading it in. Just kind of makes it a little bit quicker. You'll see, here I am back in my old family. I've got that new little family inside. We are ready to place one of these things. Go ahead, and I'm even going to place it a little bit loosely first, just so I can use my alignment tricks to go ahead and get it in the right place. So a couple things we want to do this leg. One is we want to align it, because I want the center of it to always line up with those. Okay? And because I brought it in as a separate piece, and in that separate piece it had a center, it had the left and right and front to back center. Even though you can't see that center right now, it's there. And I can use it, I can align to, from this to, there it is. Pull on over. Over here, pull on over. Okay, I'm now locked in 2 directions. So now, that table leg is going to move very nicely wherever I move. Okay, that part's very good. You say though, oh, well that's only half the story. Height isn't very good just yet. Okay. How are we going to go through and control that? Well, it turns out because we made it a part that had a parameter controlling the height, if you choose that part, the parameter is hanging right over, where to go? It's a type parameter. Sorry, it's buried alive in there. There's the table leg height. Say, okay, well that's kind of okay, but how am I going to get the value from the table leg or table bottom into table leg height? I need to kind of get those two things linked together. And how you do that is the same way we've been adding parameters. We can click on this little guy and just associate it with one of the parameters that you've already defined in the parent family. So I can say, great, that always wants to be the table bottom. Okay. Close that up. Okay, now we got a happy camper. Okay, so this thing, no matter what happens to the table top, for example, if I move that to 2 foot or 3 foot or whatever it is, okay, the table leg's going to follow. You notice the Lazy Susan hasn't followed. We didn't put anything to kind of constrain it, but we can do that later. Okay, so now you got this nice tight relationship between everything. Okay? How are we doing? We're at 6:30 now. Do you want to take like a 5-minute break? Okay, get up and stretch. Okay, let's do that. Let's take a 5-minute break. Come on back. Grab some more candy, because if not, Raj has to eat all the Twizzlers, and that's not going to be good for him. So go, be free, come back. And we'll see you in 5, and we'll finish this story up in a big bang.